All right, this is 5.2. We are going to look at doing integration of the logarithmic function. All right, so what I need you to remember is that when we did the derivative of natural log, it was 1 over x. And remember, the derivative of ln of u was u prime over u. So remember, let me write that again over here. If we had y equals ln x, dy dx was 1 over x. So what we can do is we could then go in reverse, and I'll just bring the dx over. And so the integral is your ln x plus c, okay? So there's the theorem for 5.5. So the integral of 1 over x dx equals the natural log, and because we do need natural log to be positive, remember, x has to be positive, it'll be an absolute value. So if you have some other stuff, it's the integral. You can also think of it as the integral of du over u is the natural log of the absolute value of u plus c. Okay? All right, so using the log rule for integration, the first thing I'm going to do is I'm going to pull out the 2. You can do that with a constant. And so then it's just 2 times the natural log, the absolute value of x plus c. So in example 2, what if we have a different quantity instead of x? We're going to use the u substitution and do u equals 4x minus 1. So du is 4 dx. So we don't have a 4 with our dx, so we divide. And then I'm going to rewrite this as 1/4 the integral 1 over u du. So hopefully you can see that that'll be 1/4 ln, the absolute value of u, plus c. And then we'll plug in that u was 4x minus 1. Okay? So not too bad. All right, example 3. It says find the area of the region bounded by the graph of y equals x over x squared plus 1 between the between the x-axis and the line x equals 3. So what we're going to want to do is try and draw this graph. Now the x-axis and y equals 3, let's start with x is 0. If you plug in 0, you get 0. If you plug in 1, that's 1 over 2. If I plug in 2, that's 2/5. And if I plug in 3, that's 3/10. Okay, so, and if I convert all of those to tenths so that I can really sort of see that, and you can tell if you were actually going to go beyond the line x is 3, it would continue to decrease. So let's make our y-axis go by tenths. So it's 1/10, 2/10, 3/10, 4/10, and 5/10. So I'm at 0, 0. I pop all the way up here. 4/10, and then 3/10. So I'm really looking at this region. This is the area I'm looking to find. Well, if you remember, the definition of an integral is the area of that region. So the area is going to equal, now the x values, the limits of integration, it starts at x is 0 to 3 of x over x squared plus 1. And remember, you only put the dx, that's the dummy variable, just to let you know what variable we're integrating with respect to. So in this one, I'm going to let u equal x squared plus 1. Du is 2x dx. Well, I have the x dx, but I don't have the 2, so I'm going to go ahead and divide by the 2. And then remember when we talked about changing the limits of integration, since I'm doing this, I can do it in terms of u. So instead of it starting at 0, that's going to start at 1. If I plug in that x is 3 over here, that's 3 squared plus 1, that's 10. I have the 1/2, and then it's 1 over u du. So this is not bad. So I get 1/2 the natural log, the absolute value of u, and I'm going to evaluate from 1 to 10. So this will be 1/2, and because 10 is positive, I don't need the absolute value, and 1 is positive, so I don't need an absolute value here and here. All right, well, what's the natural log of 1? We know that's 0. So I really do 1/2 the natural log of 10. If this were the no calculator part, that would be your answer. If it were calculator, you'd punch this in and get 1.151. Okay? All right, example 4 says recognizing quotient forms of the log rule. Here's the big idea. If the degree of the denominator is exactly 1 more than the degree of the numerator, then you're going to want to use u substitution with the denominator, and it'll cause you to get the log. So watch what I'm going to do. I'm going to let u equal x cubed plus x, and du will be 3x squared plus 1 dx. So here I have right here is the du. So it's 1 over u du. So that's the natural log, absolute value of u plus c. So it's the natural log of x cubed plus x plus your c. All right, letter B. If you notice, if I let u equal tangent x, du is secant squared x dx. So I would have the integral of 1 over u du. So that's just the natural log of absolute value of u plus c. That's the natural log absolute value tangent x plus c. All right, let's try it with letter C. U is x squared plus 2x. Du is 2x plus 2 dx. But if you look at that numerator, it's not quite exactly what I have over here on the right side. However, if I factor out a 2, you should notice that there's a GCF here, and I divide by that 2, then I do have my x plus 1 dx. Okay, see that? That's the x plus 1 dx. So let me substitute it then, and I have 1/2 the integral 1 over u du. And then just plug u back in. So hopefully you're seeing the pattern here. All right, let's try letter D. If I let u equal 3x plus 2, du is 3 dx. You should notice that there's no 3, so we have to divide both sides by 3. And I get 1/3 the integral, 1 over u du. It's 1/3 natural log absolute value of u plus c. And then just replace u. Okay. All right, so anytime you see the degree of the denominator is exactly 1 more than the degree of the numerator, you can do the u substitution. That'll give you the integral of 1 over u du. The other thing, like in letter B, is if you notice the denominator has the numerator as its derivative, you can use that. Okay, now, what if the degrees are equal, okay? If the degrees are equal, then we're going to need to use long division, okay? Use long division, and you'll see this. This is really cool. So the degrees are equal, and I'm going to do long division to divide. So I'm going to put times 1, and that's x squared plus 1. Now, this is going to mean that this fraction, or this quotient, I can actually rewrite this as 1 plus, and then it's the remainder over the divisor. Okay, so x squared plus x plus 1 divided by x squared plus 1 is actually equal to 1 plus x over x squared plus 1. Okay, they're just equivalent. So now I can integrate separately here and make it the integral of 1 dx plus the integral of x over x squared plus 1 dx. Okay, this first one will just be x. But over here, I'm going to need to do some u substitution because the degree of the denominator is exactly 1 more than the degree of the numerator. So we're now getting really good at this. So then this will give me 1/2 the integral, 1 over u du. Okay, so then you substitute back in. Now something I want you to think about is if I have the natural log of x squared plus 1, sometimes in the back of the book or on the AP exam itself, you'll notice they'll change the absolute value to a parenthesis. And the reason why they do that is that x squared plus 1 is always positive. So there's no need for the absolute value symbol. Okay? All right, example 6. What you notice is in the denominator, that degree is 1 more, but we'd have a problem with if we tried to expand it, that'd be x squared plus 2x plus 1, we'd be stuck. So what we're going to do is if I let u equal x plus 1 and du is dx, we're going to run into that problem that we have where there's still a pesky x up in the top. So what I can do is if I subtract the 1, I can rewrite this now as the integral of 2 times u minus 1 over u squared du. Okay, do you see what I did? I took and replaced, I solved this one for x by subtracting 1 and made it 2 times this, what x is equal to. Then this is 2u minus 2 over u squared. And then I can individually divide here and then do my simplifying. I think I can end up, this is 2 over u minus 2u to the negative 2 power. Well, then this one is going to give me 2 natural log absolute value of u. Here I would increase the power by 1 and divide by that new power. So let me continue it over here. I get 2 natural log u. It becomes a plus 2 over u plus c. And then we'll just substitute back in what u is. Okay, that one's a little bit more difficult, but let's go back through it one more time. If you substitute u is x plus 1, that's where u squared came from, and then I solved this one for x and plugged it in. Then I distributed and then broke it apart, and then I just integrated each, okay? All right. Here's the guidelines, you can read that in your notes. Then example 7. It says solve the differential equation. Remember, a differential equation just means it has a derivative of y. And what you're going to want to do is you're going to want to first separate the dy and y's and the x and dx's. So to solve it, you're going to want to integrate it. So I'm going to integrate both sides. And on the left side, I'll continue it up here, that's going to be y. But on the right side, you might think, well, you're stuck, because if I try to let u equal ln x, its derivative is 1 over x dx. But you can sort of see that you really do have that here. Let's rewrite this. Okay, 1 over x ln x is the same thing as 1 over x times 1 over ln x. So if I let u equal the ln x, du is 1 over x dx. So I really do have it here. So this is u du. So y equals the natural log absolute value of u plus c. So it's kind of weird, that's the natural log of the absolute value of natural log of x plus c. All right, example 8. If I try to integrate the tangent x dx, unless I have it memorized, I would be stuck. So I'm going to rewrite tangent x as sine x over cosine x dx. And then watch, I can let u equal cosine x. Du is negative sine x dx. Well, we don't have a negative, so we'll divide by that. And then let's do the u substitution. So I would have negative 1 over u du. So it's negative ln, the absolute value of u plus c. Well, that u was cosine x. All right. Integral of secant x. I think it's just going to be better for us to just memorize this one. This one is going to be the natural log of secant x plus tangent x plus c. And if you remember your formula sheet you're working on, I trust you're working on, these are the 6 trig ones you really ought to memorize, okay? All right, example 10. It says if you want to evaluate this integral from 0 to pi over 4 square root 1 plus tangent squared x dx. Okay, there's no way to integrate it as it is. However, if you can remember this one from pre-calculus, 1 plus tangent squared x equals secant squared x. So that's the square root of secant squared x dx. But I've changed my limits of integration. So when I plug in 0 now, the secant of 0 is 1. And if you think about the secant of pi over 4, that's square root 2 being squared, so that's 2. So this is the integral of 1 to 2. The square root of secant squared x is secant x. And then according to our chart, this is the natural log, absolute value, secant x plus tangent x. And I'm evaluating from 1 to 2. And the answer, if you do the decimal, is 0.881. All right, last one. Average value. Recall the average value formula is equal to 1 over b minus a, the integral from a to b of your f of x dx. So our average value will be 1 over pi over 4 minus 0, from 0 to pi over 4 of tangent x dx. Well, that's 1 over pi over 4. The integral of tangent x, according to our chart, is negative natural log, absolute value, cosine x. And we're going to evaluate from 0 to pi over 4. Well, 1 divided by pi over 4 is 4 over pi. and we're going to get negative natural log cosine pi over 4, it's positive, minus negative natural log cosine 0. So that's 4 over pi. This is negative natural log radical 2 over 2 plus the natural log of 1. So that's going to go to 0. And when I did the decimal, I got 0.441.